smart contracts, we will learn the following: definition and use cases of smart contracts, basic programming for smart contracts using languages like Solidity for Ethereum, creating and deploying simple smart contract. Definition and use cases of smart contracts. A smart contract is a self-executing contract with the terms of the agreement between buyer and seller directly written into a code. It automatically enforces the terms when predefined conditions are met, eliminating the need for intermediaries. Smart contracts are typically built on blockchain platforms, ensuring transparency, security, and immutability. Following are the use cases. Decentralized finance, DeFi. Smart contracts enable lending, borrowing, trading, and yield farming without traditional financial intermediaries. Supply chain management. Automate and track the movement of goods across its supply chain, ensuring transparency and reducing fraud. Voting systems. Created secure and tamper-proof voting systems, ensuring fair elections and transparent results. Real estate transactions. Automate property transfers, escrows, and payments while reducing the need for intermediaries. Digital identity. Establish secure and portable digital identities, reducing the risk of identity theft. Gaming. Implement variable ownership and transactions of in-game assets. Insurance. Automatically trigger insurance payouts based on predefined conditions. For example, flight delays. IoT, Internet of Things. Enable devices to interact and transact autonomously. For example, energy trading. Programming smart contracts using Solidity. Solidity is a programming language used for writing smart contracts on the Ethereum blockchain. The basics are, essentially, this is nothing more than object-oriented programming. Contracts are the primary building blocks containing data functions. Function execute action, while state variables store data on the blockchain. Here is the structure of the contract with the contract example, constructor, and function. In order to deploy a smart contract, you need to use a development environment like Remix, which you can see, compile the code, and then deploy the contract. In order to interact with smart contracts, you can interact with them using their address, use a Web3 library to communicate with the Ethereum network, call function, and access state variables through transactions or constant calls. Secure code. Remember, working with smart contracts and blockchain development involves a learning curve, so take your time to understand the concepts thoroughly. We have presented a very high-level view, but if you're interested in learning more, do let us know in the comments. Blockchain security, we will learn the following: cryptography fundamentals and its roles in blockchain security, cryptocurrency consensus algorithms, which include proof of work, proof of stake, delegated proof of stake, blockchain vulnerabilities and attacks, and best practices for blockchain security. Cryptography fundamentals and its roles in blockchain security. Cryptography is the foundational element of blockchain technology, providing security and privacy in the decentralized ecosystem. Here are some of the key cryptographic concepts and their roles in blockchain security. Hash functions. Hash functions convert input data into a sized string of characters called hash in a way that's nearly impossible to reverse. In blockchains, hash functions are used for data integrity, as even a small change in input results in drastically different hash. Digital signatures. Digital signatures ensure the authenticity and integrity of messages. In a blockchain, transactions are signed with private keys, and anyone can verify the signature using the corresponding public key. Public key cryptography. Public and private key pairs are used for secure communication and authentication. Participants in a blockchain network have public addresses derived from their public keys to receive transactions and sign them with their private keys. Symmetry and asymmetric encryption. These methods, like AES and RSA, are used to secure communication between parties. Asymmetric encryption is particularly useful for key exchange and data privacy. Cryptocurrency consensus algorithms. These algorithms determine how participants in the blockchain network agree on the state of the blockchain. Here are some of the notable ones. Proof of work. Miners solve complex mathematical puzzles to validate transactions and create new blocks. The first miner to solve the puzzle gets to add the next block and is rewarded with cryptocurrency. Proof of work is energy intensive but highly secure. Proof of stake. Validators are chosen to creating blocks based off the amount of cryptocurrency the stack lockup as collateral. Proof of stake is energy efficient compared to proof of work, and it's based on the concept that those with more stake have more incentive to behave honestly. Delegated proof of stake. In DPoS, token holders vote to select a smaller group of delegates who have the responsibility of validating transactions and producing blocks. This approach aims to increase scalability by reducing the number of validators. Now let's move on to blockchain vulnerabilities and attacks. 50% attack. An attacker controls more than 50% of a blockchain's mining power, allowing them to manipulate transactions, double spend, or rewrite history. This attack is more likely in smaller blockchains with low mining power. Double spending. A user spends the same cryptocurrency twice by creating two conflicting transactions. Blockchain's proof of work mechanism minimizes this risk to avoid double spending. Sybil attack. An attacker creates multiple fake nodes to gain control over a network. This determines decentralized consensus. Smart contract vulnerabilities. Bugs in smart contract code can lead to unintended behaviors. The DAO hack in Ethereum is a famous example. When an attacker drains a scientific amount of Ether by exploiting a vulnerability. Best practices for blockchain security. Use strong cryptography. Utilize robust cryptographic elements, algorithms, and libraries for key management, encryption, and digital signatures. Secure key management. Safeguard private keys in hardware, wallets, or secure environments. Avoid storing them online. Regular code audits. Continuously review and audit smart contract code to identify and fix vulnerabilities. Network security. Secure nodes API to communication channels to prevent unauthorized access. Consensus mechanism selection. Choose an appropriate consensus algorithm that suits the security needs and goals of the blockchain. Regular updates and patches. Keep software protocols up to date to address known vulnerabilities. Educate users. Educate participants about phishing attacks, secure wallet practices, and overall blockchain security. Test on testnets. Before deploying to the mainnet, test smart contracts and applications on testnets to identify issues. Governance and upgrades. Implement upgrade mechanism and governance processes to respond to security issues. Blockchain security is an evolving field, hence staying informed about the latest developments and best practices is essential to ensuring the safety and integrity of blockchain networks and applications. Use cases and applications of blockchain. We will learn the following. Real-world applications of blockchain beyond cryptocurrencies, for example in supply chain, healthcare, finance, etc. Case studies of successful blockchain implementations of real-life scenarios. So let us get started. Blockchain technology has applications beyond cryptocurrency, and now we will review some real-world use cases of blockchain. Supply chain management. Blockchain can be used to enhance transparency and traceability in supply chains, reducing fraud and ensuring the authenticity of products. Case study. Walmart and IWM. Walmart and IWM collaborated on using blockchain to track the movement of pork products in China. This allowed for real-time monitoring of the product's journey from farm to store, ensuring food safety and quality. Healthcare records. Blockchain can securely store and share patient data, enabling protecting sensitivity medical information. Case study. MedRec project. The MedRec project at MIT developed a blockchain-based system for managing medical records. Patients could grant permission to healthcare providers and researchers, ensuring data security and privacy. Voting systems. Blockchain can enhance the security and transparency of voting systems, reducing the potential for voter fraud. Case study: West Virginia's 2018 midterm elections. West Virginia piloted a mobile voting platform called VoteSee, which utilized blockchain to allow military personnel stationed abroad to securely cast their votes. Digital identity verification. Blockchain can provide individuals with control over their digital identities, reducing the risk of identity theft. An example is digital identity verification. Blockchain can provide the ability to allow users to control their personal information and selectively share it with trusted parties. It was used in Switzerland e-voting pilot. Intellectual property protection. Blockchain can create a tamper-proof record of intellectual property rights and transactions, helping artists and creators protect their work. Case study: Scribe, which is a blockchain-based platform. It helps artists and creators prove ownership of their digital creations and track their usage across the internet. Smart contracts. Blockchain-based smart contracts enable self-executing agreements with predefined conditions, automating processes and reducing the need for intermediaries. Case study: Solike and the DAO, Decentralized Autonomous Organization, aim to create a venture capital fund controlled by token holders. However, due to vulnerabilities in the smart contract code, a significant amount of funds were drained, highlighting the importance of secure coding practices. Real estate transactions. Blockchain can streamline real estate transactions by providing a secure and transparent way to transfer property ownership. Case study: ProPi. ProPi is a blockchain-based platform that facilitates international real estate transactions. It allows users to buy properties online and ensures transparent property transfer. Energy trading. Blockchain can enable peer-to-peer energy trading and management within microgrids, reducing reliance on traditional energy distribution systems. Case study: Brooklyn Microgrid. The Brooklyn Microgrid project allows neighbors to buy and sell excessive solar energy using blockchain-based smart contracts, creating a local energy marketplace. These case studies illustrate the diverse applications of blockchain technology beyond cryptocurrencies, showcasing its potential to revolutionize various industries by improving transparency, security, and efficiency. Blockchain development. We will learn the following: setting up a development environment for blockchain projects, developing decentralized applications, interacting with blockchain networks using APIs and SDKs. We will focus primarily on Piri, however, towards the end we'll get into some Python example. So let's get started with blockchain development basics. Programming languages. Blockchain development involves coding smart contracts, decentralized applications, and more. Common programming languages include Solidity for Ethereum, JavaScript for dApps, and languages specific to blockchain platforms like Chaincode. The following are the blockchain platforms. Ethereum. It is known for its smart contract functionality. Ethereum allows developers to create decentralized applications on its blockchain. Hyperledger Fabric, a permissioned blockchain platform designed for enterprise use cases, offering more control over who can participate. There are various other blockchain platforms, each with its own features and use cases, for example, Cardano, Binance Smart Chain, etc. Smart contracts. These are the self-executing contracts with the terms of the agreement directly written into code. Smart contracts automatically execute actions when predefined conditions are met. Solidity is a popular language for writing smart contracts on Ethereum. Decentralized applications, also known as dApps. dApps are applications that run on a blockchain network rather than on a centralized server. They aim to provide transparency, security, and user control. dApps can be built using various programming languages and frameworks. The development tools that are used are Truffle, a development framework for Ethereum, simplifying smart contract development, testing, and deployment. Remix, an online Solidity IDE for writing, testing, and debugging smart contracts. Web3.js, a JavaScript library for interacting with Ethereum-based applications for web browsers. MetaMask, a browser extension wallet that allows users to interact with Ethereum dApps. There are also various tools that you can use based on your need of the application, but these are some of the good examples of it provided. Let's get into steps in blockchain development. Step 1. Idea and design. Define the purpose of your blockchain application, design its architecture, and plan the smart contracts logic. Step 2. Development. Write the code for your smart contracts and any necessary backend front-end components. Step 3. Testing. Thoroughly test your smart contracts and the entire application for security vulnerabilities and functionality. Step 4. Deployment. Deploy your smart contracts to the chosen blockchain network, for example, Ethereum's mainnet or testnet. Step 5. User interface. Develop the user interface of your application as one, ensuring it interacts seamlessly with the blockchain backend. Step 3. Security audits. Consider getting a third-party security audit to identify and mitigate potential vulnerabilities. Interacting with blockchain networks using APIs, which are application program interfaces, and SDKs, which are software development kits, is a crucial aspect of blockchain development. APIs provide a way to communicate with blockchain nodes and retrieve or submit data, while SDKs offers libraries, tools, and utilities to simplify the process of interacting with the blockchain network. Let's explore how to interact with blockchain networks using APIs and SDKs. Number 1. Choose a blockchain network. Decide which blockchain network you want to interact with. This could be Ethereum, Spotchain, Hyperledger Fabric, or any other blockchain platform. Different networks have different APIs and SDKs available, so your choice will depend on the project's requirements. Number 2. Select the right API or SDK. Once you have chosen the blockchain network, identify the relevant APIs or SDKs that provide the functionality you need. For example, Web3.js, a JavaScript library for interacting with Ethereum and Ethereum-compatible blockchains. Ethers.js, another JavaScript library focused on Ethereum interactions. Smart Chain API. Binance provides API documentation for interacting with their blockchain. Hyperledger Fabric SDKs. Hyperledger Fabric offers SDKs in various programming languages like Node.js, Java, and Go. Number 3. Set up your development environment. Install the necessary libraries or SDKs in your development environment. This may involve using package managers like npm for Node.js or Maven for Java. Number 4. Interacting with blockchain. Reading data. Retrieve blockchain data like account balances, transaction history, and smart contract states. Use API endpoint or SDK functions to query data from the blockchain node. Writing data. Submit transactions to the blockchain, such as sending cryptocurrency or invoking smart contract methods. Construct transactions using APIs or SDKs. Sign them with private keys and send them to the network. Smart contract interactions. Load smart contracts using the addresses and API, also known as application binary interface. Whole smart contracts method is using APIs or SDKs to perform actions on the blockchain. Number 5. Handle errors of security. blockchain interactions involve potential risks and challenges, such as handling errors, managing private keys securely, and protecting sensitive data. Make sure to implement error handling, manage your keys properly, and follow best practices for security. Number 6. Test and debug. Before deploying your application to the mainnet, use test networks like Ethereum's Bobstan or RingBi to test and debug your interactions. This prevents unintended financial losses and ensures your code functions as expected. Number 7. Documentation and resources. Refer to the official API or SDK documentation for detailed information on available methods and parameters. Online tutorials, forums, and developers community can provide guidance and support as well. Now let's cover a topic of Python. We have covered Python in detail in this channel already. Python for Course Beginners course link shared in the description as well. Now we will focus on creating a simple blockchain using Python. This tutorial will cover the fundamental concepts of a blockchain, including blocks, hashing, and validation. Please note that this is a very simplified example for educational purpose. Step 1, as you can see on the screen, you create a blockchain class, simply a block class, and gets created using Python representing a block in the blockchain. Each block will have an index, timestamp, data, previous hash, and its own hash. Step 2, create a blockchain class. Create a class to manage the blockchain. Initialize it with the Genius block. Step 3, test the blockchain null. Let's create a simple blockchain and test its functionality. This tutorial provided a basic introduction to blockchain concepts and a simple implementation of Python. Real-world blockchains are much more complex and involving advanced cryptography, consensus mechanisms, and network consideration, but as we're in the comments if interested in learning more. Blockchain governance and regulation, and we will learn the following. Exploring the regulatory landscape for blockchain and cryptocurrencies, governance models in blockchain networks, legal and ethical considerations. So let us get started. Number 1, regulatory landscape for blockchain and cryptocurrencies. The regulatory environment for blockchain and cryptocurrencies varies significantly across different countries and regions. It is important to note that regulations are still evolving and can impact various aspects of blockchain ecosystem, such as initial coin offerings, security tokens, decentralized finance, and much more. Key regulatory considerations include security laws. Many governments consider certain cryptocurrencies or tokens as securities subject to existing security laws. This impacts ICOs and token sales. Anti-money laundering and know your customer. Cryptocurrency exchanges and business dealings with cryptocurrencies are often required to adhere to AML and KYC regulations to prevent illegal activities. Taxation. Cryptocurrency transactions may be subject to strict taxation. Different areas treat cryptocurrencies as property, currencies, or something else for tax purpose. Consumer protection. Regulation focuses on protecting consumers for fraud, scams, and misleading practices in the blockchain and cryptocurrency space. Licensing and registration. Some countries even require businesses dealing with cryptocurrencies to obtain license or registration. Number 2, governance models in blockchain networks. Blockchain governance refers to the decision-making process within a blockchain network. It involves establishing roles, protocols, and mechanisms for managing upgrades, changes, and conflicts. There are several governance models. Centralized governance. A single entity or organization that has authority to make decisions and changes. This model lacks decentralization but can lead to a quicker decision-making. Decentralized governance. The decision-making power is distributed among various stakeholders, often through voting mechanism. Proof-of-stake and delegated proof-of-stake networks often use this model. Hybrid governance combines elements of both centralized and decentralized governance to strike a balance between efficiency and decentralization. On-chain governance. Decision-making is encoded directly into the blockchain protocol through voting mechanism and smart contracts. Off-chain governance. Decisions are made outside the blockchain through discussions, forums, and other communication channels. Changes are then implemented on-chain. Number 3. Legal and ethical considerations. Legal compliance. Blockchain projects must adhere to relevant laws and regulations in their jurisdiction, which can include securities laws, AML regulation, tax laws, and more. Privacy. Ethical concerns regarding user privacy and data protection arise when blockchain transactions are immutable and publicly accessible. Some projects incorporate privacy-focused technologies. Interoperability. Ensuring that different blockchains can communicate and share data ethically and securely is important for the overall health of the blockchain ecosystem. Environmental impact. The energy consumption of some blockchain networks, especially those using proof-of-work consensus, raises ethical questions and environmental sustainability. Decentralization and censorship resistance. Ethical considerations include maintaining the principles of decentralization and censorship resistance, as those are often more needed from the blockchain technology. Blockchain future trends and innovation. We will learn the following. Emerging blockchain technologies, DeFi, NFTs. Blockchain's potential impact on industries and society. So let's get started. Emerging blockchain technologies. DeFi, decentralized finance. DeFi refers to a range of financial applications built on blockchain technology that aim to provide traditional financial services such as lending, borrowing, trading, and yielding farming without intermediaries. DeFi platforms operate through smart contracts and enable greater access to financial services globally. NFTs, non-functional tokens. NFTs are unique digital assets that represent ownership of a specific item, piece of content, or artwork. They have gained significant attention in the art, entertainment, and gaming industries, allowing for new monetization and ownership models. Blockchain interoperability protocols. These protocols facilitate communication and data exchange between different blockchain networks. They aim to solve the issue of blockchain silos by enabling seamless interactions across multiple blockchains. Examples include Polkadot, Cosmos, Ion. Scalability solutions. As blockchain networks like Ethereum face scalability challenges, high transaction fees, and slow confirmation timelines, solutions like Layer 2 scaling, such as optimistic rollups and Plasma, and newer blockchains, are emerging to address these issues. Blockchain and supply chain management. Blockchain can enhance transparency and traceability in supply chains by recording every step of a product journey, reducing fraud and ensuring authenticity and improving efficiency. Blockchain's potential impact on industries and society. Finance and banking. Blockchain has the potential to disrupt traditional financial systems by reducing the need for intermediaries, enabling faster cross-border transactions, providing access to financial services for the unbanked and underbanked populations. Healthcare. Blockchain can enhance data security, interoperability, and patient privacy in healthcare systems by enabling secure and transparent sharing of medical records and other sensitive information. Supply chain and logistics. Blockchain's ability to create an immutable record of a product's journey from raw materials to the consumer can improve transparency and streamline supply chain processes. Real estate. Blockchain can simplify real estate transactions by creating a tamper-proof digital record of property ownership, reducing paperwork, fraud, and the need for intermediaries. Voting systems. Blockchain-based voting systems can enhance the security, transparency, and integrity of legal elections, potentially reducing voter fraud and increasing voter turnout. Intellectual property and content creation. NFTs enable artists, creators, and content producers to monetize their digital creation, granting them more control over their work and revenue streams. Energy and sustainability. Blockchain can help in creating transparent and traceable systems for tracking energy consumption, verify carbon credits, and promoting sustainable practices. Before we wrap up, let's focus on the challenges and considerations. Scalability. As blockchain networks become more popular, scalability remains a significant challenge to ensure smooth and efficient transaction processes in terms of regulation, valuation of potential speculative bubbles, wealth distribution. As with any disruptive technology, there's a risk that early adopters and those with access to resources will benefit more, potentially raising the gap between the wealthy and the poor. Smart contracts and automation. The use of smart contracts can automate processes and reduce reliance on intermediaries. This can lead to streamlined operations but raise questions around accountability when things go wrong due to vulnerabilities. Ethical implications. Environmental impact. Proof-of-work blockchains like Bitcoin consume significant energy resources. This raises concerns around the environmental impact of technology and the need to transition to more energy-effective consensus mechanism. Token value speculation. The speculative nature of cryptocurrency markets can lead to excessive price volatility and risk for investors. This can affect the financial well-being of individuals who might not be able to understand the risks involved. Digital ownership and cultural heritage. NFTs raise ethical questions about the ownership of digital art and cultural artifacts that intersect with the discussions around culture appropriateness and the rights of communities. Transparency and immutability. While immutability ensures integrity of records, it can also create ethical dilemmas if incorrect or harmful information gets permanently stored on a blockchain. It's important for individuals, businesses, and policymakers to consider these implications as blockchain technology is integrated into various aspects of our lives. A multidisciplinary approach involving technologies, economics, and legal experts is necessary to address these challenges and ensure that blockchain technology benefits society as a whole.